So, we were looking at last class the flux cooled arc welding. So, we looked at the various fluxes that we use in flux cooled arc welding or in metal arc welding electrodes, right. So, we looked at the rutile based electrodes, the basic electrodes, cellulosic electrodes, and we looked at the chemical reaction that actually produces the shielding gases. So, in rutile based electrodes, the hydrogen is primarily generated by the moisture decompositions leading to generation of hydrogen in the surface of titanium oxide, for example, and then cellulosic material, carbon monoxide, carbon dioxide generation, and in basic electrodes, disintegration of calcium carbonate leading to generation of carbon dioxide, and we looked at metal transfer behavior. And rutile based electrodes, because of the influence of titanium oxide and the fluxes on the surface tension, so the metal transfer will be mostly globular, where the droplet size is much finer, and then we have very steady state spray transfer achieved in rutile based fluxed containing electrodes. So, whereas in basic electrodes we do not have that luxury of transferring the droplet like in the rutile based electrodes. In basic electrodes is mostly repelled globular, and most of the time we may also have unburned fluxes forming in the fingers at the tip of at the center of the electrode. Okay, so, we looked at various modes of metal transfer in a video, okay, in while welding and self shielded flux cooled arc welding electrodes, right. Self shielding means again we do not use external shielding gas. Shielding gas is generated while burning the flux. So, I showed you a video, couple of videos where self shielded electrodes, basic electrodes which generates carbon dioxide CO2 while burning, and then the metal transfer is primarily repelled globular transfer, is not it. And then we stopped the last class at the slide where I showed you the advancements that are made in GMAW. Okay. So, we looked at the one slide. Okay. So, we will see elaborately in this class some of the advances that are made to make the process much more stable, right. So, one such advantage is the pulsed GMAW. So, I already indicated the use of current pulsing in metal transfer characteristics, right. So, when you look at the behavior of metal transfer as a function of current, our objective to achieve the stable process characteristic is to achieve a drop spray transfer, isn't it. So, we will have to get a spray transfer so that the productivity increases. We transfer the enough volume of liquid metal to the weld, but the transfer should be made in such a way that the droplet diameter is equal to the filler diameter, the electrode diameter, or slightly lower than that. Okay. And then we will have to continuously transfer the droplets, right. So, that can be achieved just above spray transition current, right. If we keep the current above the spray transition, then we can achieve the spray transfer in drop by drop mode, right. That is what we call it as a drop spray transfer. So, if you look at in a constant current GMAW, we will have to increase our current above spray transition to achieve this kind of spray transfer which we require for stable GMAW. The same transfer can also be achieved instead of using a constant current by using a pulsed current. Okay. So, in pulsed current what we do is, so suppose if you look at time versus current. So, in a conventional so GMAW, in order to achieve the spray transfer, so in a conventional transfer, so you may have some mean current, isn't it, a constant current in a conventional GMAW where we have you can be constant DC, right. So, instead of using a constant current, and we can use a pulsed current, in which so you have a current pulsing where your maximum pulse current can be much higher than your current needed for the constant current case. Okay. And then we will bring it back immediately to some value and then maintain at a background level, and then again we will do a pulsing, and then the cycle can continue further. Okay. So, in this case advantage of using such pulsing is we reach a much higher current than the spray transition current during pulsing. So, this is known as the pulse current. So, by doing so we can form a droplet, and then because of the high current we supply can create enough Lorentz force in such a way that the droplet can be transferred one droplet per pulse. Okay. So, during this IP period, so this is a pulsing period Tp. Okay. So, during this Tp we increase the current to IP, and then one droplet can be detached, and immediately the current can be decreased to a background level, which is IB. So, in this case, so we can either maintain a very small arc, okay, so arc with very low power, and this background current can be sufficient for maintaining a low current arc, and then we give some time interval, which is Tb background current, and then immediately you can raise the current to again the IP to detach the another droplet. Okay. So, now advantage of doing this is if you take an average the current over one cycle is one cycle time. What is one cycle time in this case? Is Tp plus Tb, isn't it? If you take the average current over this one cycle, okay, it will be much lower than the current what you use in a constant current case, isn't it, right. So, if you look at the average current, how do you calculate the average of the cycle? Suppose if you want to calculate the I mean, IP times Tp plus IB times Tb divided by Tp plus Tb, exactly. So, if you calculate the average I mean, it will be much lower than what you use in constant current case. That means that the amount of heat arc energy you generate will be lower than when you use a constant current, but by doing lower current you can still achieve a spray transfer, isn't it. So, you can achieve a stable spray transfer by supplying an average current much lower than, so when you use a constant current throughout the welding process. Okay. So, your heat input or arc energy decreases significantly without compromising your productivity and the process stability. Okay. So, such kind of waveforms are very widely used to achieve a spray transfer on GMAW process, and by doing so you also reduce the amount of heat you put in the material while welding. So, the other advantage over here is, so you minimize the damage you do to the base material because you reducing the heat input or arc energy significantly without compromising the transfer characteristics what you achieve otherwise you use a constant current, right. And by carefully controlling the power source characteristics we can achieve a one drop per pulse. So, by carefully selecting the frequency of the pulsing frequency, we can also determine how many droplets you want to detach per second, isn't it. Suppose if you are applying a 50 hertz of pulse, okay. So, number of pulse is 50 per second. So, you get 50 droplets per second, okay. So, over this pulsing cycle, right. You can increase the pulsing number of frequencies, you can increase subsequently, but that is depending on the power source characteristics. So, by using a modern rectifier inverter based power sources using a microprocessor control, and we can achieve such a waveforms very easily, right. It is clear. So, we will see in this class. So, how do we choose these pulsing parameters? Okay. So, what is so special about it? We look at the videos obviously. So, look at when we are doing a pulsing how the transfer takes place, right, and then some calculations to identify this IPTP for a given material, right, and then we will move on to the next advancement. in GMAW. Okay, it's good. Any questions so far? Then we will go to the slides. Then it will be clear even more. Okay, so the three, in fact, two advancement I want to cover here, which is very widely used nowadays in industry, is the pulse GMAW. The second is the controlled dip transfer. Okay, so the controlled dips transfer, it is now known in various names. So most commonly used variant of controlled dip transfer is cold metal transfer. Okay, so cold metal transfer welding, which is another variant of the controlled dip short circuiting transfer, where we play around with the waveforms, because when you do a short circuiting transfer, there are some inherent problems the moment you have a short circuiting. So what are the problems? For example, when you have a short circuiting event takes place, immediately your voltage becomes close to 0. Okay. So then your current is passed in a system which is voltage is 0. Okay. So that means that you create enormous amount of Lorentz force plus Joule heating of the electrode. Okay. So when you have uncontrolled current passing through when the short circuiting happens, the droplet develops enormous amount of Lorentz force as well as the magnetic field, which may cause the droplet to explode, and that can cause a serious turbulence in the well pool, and that exploding droplets and the well pool can cause a severe spatter. So then your well quality decreases significantly, because you create a spatter as well as the explosion can lead to a well pool turbulence, and then the well stability decreases. So in order to achieve a stable transfer during the short circuiting event, people thought about it and then they modified the waveforms in such a way that when the short circuiting happens, we can minimize the current by detecting the voltages, and then we can manipulate the wire movement back and forth in such a way that we can achieve a drop transfer in extremely low heat input by manipulating the waveforms. In fact, we can transfer droplet at the melting temperature of the droplet, okay, by controlling the dip transfer, right. So that is why these two are very widely used nowadays in GMAW, gas metal arc welding, the pulse GMAW, and then the controlled dip transfer, which is known in various brand names. One of the brand name is cold metal transfer. So we look at these two. And then these two, the process is possible by the advancement in the power source, okay. And this one such advancement which is widely used for achieving the pulsing and the controlled dip short circuiting transfer is synergy power sources, okay. So we look at what is synergy mean, and then how the synergy power source is widely used to achieve this advancement in GMAW, okay. Good. So we will move on. The first pulsed GMAW. So as I explained in the first slide, so what we are trying to do is, instead of using a constant current, okay, so we do a pulsing current, and during this pulsing period we make sure that one droplet detach from the electrode by subjecting a much higher peak current, okay. And then we maintain a background current during this process, and in this case we maintain a very small arc, make sure that arc is there, otherwise you will have to apply an high frequency ignition, okay, so during this period. So we maintain an IB in such a way that an arc is stable, and then subsequently we can do another pulsing and then achieve subsequent droplet transfers, okay. So by doing so, the total average I mean decreases significantly. For example, 1.2 mm carbon steel, so if you achieve a drop spray transfer is about say 200 amperes, you could achieve by pulsing in as low as 70 amperes, the similar transfer characteristics, okay. So the I mean can be as low as 70 amperes. So you can choose by playing around the IP, the peak current and the background current, and then peak time and the background time, we could achieve absolutely similar transfer characteristics at as low as 70 amperes. So that is advantageous, okay. So because we are also not consuming energy, and your transfer characteristic are much nicer than when you use a constant current, and you also have a very stable process at a very low heat input, right. So, we will see the video of this process and then we will go to the physics of it, right. Okay, good. So, we will have to achieve a drop spray transfer. So, the characteristic of drop spray transfer is the droplet should be detached with a diameter similar to the filler, and then it has to be continuous. You see that, so the arc is there is a background arc, and we are transferring the droplet 1 per pulse. So, when the pulse is given, arc glows and then you form a droplet, and then droplet is formed and then it is detached because of the pulse current, right, is clear. And then subsequently when the pulse is stopped and you may maintain a background arc, and then the cycle can be continuously applied to get the droplet detached continuously. So, number of droplet detached is determined by the pulsing frequency. If you give 50 pulses, obviously if you detach 50 droplets per second. So, we will have to carefully choose the IP and TP and similarly background current, and which will be characteristic of the melting wire, the composition as well as the shielding gas that you use, because that will determine the amount of heat that is transferred to the tip to melt, is not it. Melting rate is determined again by the heat in the electrode, the heat supplied from the arc to the electrode, right. And then if it is an anode, so you have 2 other parameters, right. What are the parameters? Come on guys, melting rate, the work function, so the amount of energy gained, is not it, right. And then that will determine whether it is positive or negative, right, in the anode. And then we will have a latent heat contribution and the latent heat of melting contribution, right, it is clear. So, once you know the melting rate, which is extremely important in this case, because so we will have to maintain the arc length constant, is not it, the length over here from here to here, it is constant. That means that, so we will have to calculate your melting rate in such a way that we can also feed the wire at a similar rate, right. So, then how do we calculate the melting rate here? So, we will have to first calculate the I mean based on the formula, the average formula, and then once you know the I mean, then we can also calculate from the same equations. So, alpha I mean plus beta, okay, L I mean square divided by pi r square, right, it is clear, right. But now how do we choose IP and TP? We can't choose randomly, right. So, there must be some relationship, right, for a given material, and we will have to identify how do we arrive at the pulsing parameter, right, then we can do that, okay. So, we can also get the pulsing parameter predicted for a given material of diameter, whatever we need, right. So, we will quickly go on, okay. So, this is clear, right. So, we transfer a droplet per pulse, right, it is clear. The objective of this pulse GMAW to achieve a spray transfer at mean currents much lower than the spray transition current, otherwise we use it for the constant current GMAW. And we maintain a small background current to have an arc, otherwise you will have to apply an high voltage or high frequency ignition during that period, and that may cause instability. And during pulsing we increase the current much higher than your spray transition current, so that we melt the tip and then transfer the droplet by the increase in Lorentz force. Yes, it is clear, good. So, this process is known to get a very stable transfer than the constant current GMAW, okay. So, because of the increased pulsing current, and we definitely detach the droplet, okay, because of the increasing current which is generated, because when E increases the arc energy is also increases, is not it, because if you look at the V column, I, obviously if I increases, the arc energy is also increases significantly. Okay. So, in that case the amount of heat is transferred from the arc to the electrode tip also increases significantly. So, you melt immediately, you form the droplet, and the moment droplet is formed, Lorentz force would pull the droplet down, right, it is clear. And then you do not keep it at that current level for a long time. If you keep it at that current long time, obviously what happens? Jetting spray would happen, is not it, because it is much higher than the spray transition, right. So, if you keep it the pulsing duration very long enough, then you will start detaching droplet in jetting spray mode, because the current is much higher than the spray transition, right, it is clear. So, carefully playing around with the pulsing current IP and then background current, we can achieve extremely stable process, achieve metal transfer characteristic which is very needed for stable GMIW process, right, it is clear. So, this video we already seen. So, we have a transfer carried out in a pulsed GMIW process. So, there are some relationships we can use. So, generally for a given material, the IPTP is a constant. Okay, so, that is a function of material composition and the diameter, and we will come back to that. So, when you are calculating the pulsing parameters. So, the IP is the pulsing current which is always higher than the spray transition current, much higher than the spray transition current, okay, and D is detachment constant, okay. So, and then IB is a background current, and that has very little influence on detachment, because detachment has already happened before the onset of IB, okay, it is clear. And then the relationship generally N varies from 1.1 to 2, in most of the material we can make that as a constant, and D is a function of material composition and the diameter, right, it is clear. And then we can establish for a given material such a process window. So, the process map we can generate for a given material, where the pulse amplitude is IP and then pulse duration which is Tp plus Tb, right. So, we can get the pulse duration as a function of pulse amplitude, and which would give us a stable one transfer per pulse, that is our criteria, right. If you look at the videos, we will have to make sure that one droplet should come per pulse during the cycle period, and if for example at a higher pulse duration period, it has to be in this range, okay. So, if it is lower than that, the current, right, the current is very low, so you may not detach. So, you may have detachment happens with the much larger droplet diameter, because the gravity should do the job, because of the lower current mass has to be created, then only the gravity can detach the droplet. If the current is much higher at longer duration, you may get more droplets, right, per pulse, because you keep keeping it for a very high current for longer time, that means that you get more droplets per pulse. Similarly, at shorter duration, you need to have a longer current to achieve one droplet, and if it is lower, then you may not get the condition stable transfer, right. You may again get higher than the spray transition, right. So, we can achieve such a process map, and which is extremely important for a material, right. So, for example, this graph is generated for 1.2 mm diameter carbon steel wire with argon plus 5% CO2, and then there is a condition that one droplet per pulse. And these information, they are there in the power source nowadays, okay. So, without the information we cannot arrive at the pulsing parameters, right. So, the advancement power sources what we talked about in the microprocessor controlled the power sources, and these are the information we generate by carrying out the fundamental experiments and then supply to the power source system, and the power source can choose, suppose if it wants to use a mean current of, for example, 200, then it has to calculate what will be IP and TP, IB and TB, for a given IM, so that it gets 1 droplet per pulse. So, immediately you will do all the calculations and then identify what will be the wire feed rate, right, to maintain the constant arc, right. So, all the calculation it has to do and then give the process parameters and the wire feed rate to weld and achieve the stable transfer, right. It is clear. Okay. So, how does this calculation takes place? Okay. So, what are the parameters we need? So, we first we need to identify such a maps. For example, we need to identify, so what will be the pulsing current and then Tp pulse duration, and then we can identify for a given material and wire diameter. So, various compositions we will get these parameters. So, Ip, Tp, and then we constantly change and identify which current will give a stable one pulse transfer for a given pulse. Okay. So, this information it's already we can generate readily, and then this goes into power source, and then we can do some calculations. So, these are all very basic simple physics, right. So, suppose if you want to maintain the constant arc length, okay. So, this is my arc length. Okay. So, this should be constant. So, that means that the melting rate should be equal to wire feed rate, isn't it. So, you supply what you melt. So, then the arc length becomes constant, right. And suppose if you are transferring at one pulse the length LD of the material, okay. So, then basically the wire feed rate is equal to the frequency of pulsing times the length of the wire you transfer, you melt, isn't it. So, what is F? F is the frequency, right. So, that is nothing but the unit is mm per second, isn't it. So, basically how much mm you transfer in a second, that is wire feed rate, right, isn't it. What is per second? Here is a frequency, right. So, frequency is number of pulses per second, because you transfer one droplet per pulse. So, this is a relationship we have, right, and then we have I mean relationship. So, what is I mean? The mean current, which is IPTP, IBTP by IP plus TP, and simple average, isn't it. So, when you have a pulsing current, right. Now, these two we have, and then we can select the pulsing parameter with these two. How do you do that? So, first we need to get an IP and TP from the relationship, the process window. The condition is I need 1 droplet per pulse, right. So, that is a criteria, and then you choose any mean current, I mean. Okay. So, any I mean current we can calculate the wire feed rate, isn't it. How do you calculate the wire feed rate? Alpha I plus beta L IM square by pi r square, isn't it. Because I mean is this relationship, okay, but we can calculate the wire feed rate, right. So, once we know wire feed rate, we can also calculate from the wire feed rate the frequency f, because what is the relationship between f and frequency, isn't it, and the Doppler diameter, it is the fellow wire diameter, we can assume, isn't it. Or we can also establish the relationship between the wire feed rate versus frequency, and you can choose. So, what will be WF relationship. So, we can choose the F from the W. Once you know F, we can calculate what is the background time we need, because we know IP and TP, we know TP already, isn't it. So, we can get TB, which is nothing but, so TP plus TB is equal to 1 by f, isn't it? Is it not? That is a frequency. So, f is equal to 1 by Tp plus Tb. So, from that we know Tb, we need to know Tb because background current we do not know. So, f we know from W, W we know from Im, isn't it? So, Im we know from the relationship 1 droplet per pulse, right. So, once you know the Tb, all the unknowns are now known except the background current, isn't it? The background current can be solved from the equation. So, we know Ip and then we know Tp, we know Tb, the only unknown is Ib, Ib calculated from the average equation, right, good. So, these all calculations are done in power source nowadays. Okay, so, when you want to establish your own pulsing parameters, we will have to do all these calculations by ourselves. So, that is what when you are now buying the power source, the company they also sell the welding parameters and you will have to pay for that. Okay. So, suppose if you want to weld an Inconel 625 using pulse GMAW, and you can you have to contact the power source manufacturer and they will give you a simple program, and that program you need to load to the power source, and that program contains all the calculations. Okay. And then it will also identify what diameter you will use, because diameter is very critical because that determines your LD. So, for a given LD, okay, so you will have to identify W, and W again is determined by the compositions, because composition contains your H, Cp, right, isn't it? Latent heat of melting is there and then Cp is there, that will be used to calculate the melting rate, isn't it? So, melting rate, then once you know melting rate, and we will also need to keep the constant arc length. So, the wire feed rate is identified, right. And then for a given composition the database also contains. So, what will be the relationship between Ip and Tp, the process map I showed you, the graph. So, once you have the Ip and Tp is known, W is known, F is known, and then Tb is also known. Once you know Ip, Tp, Tb, you can also call Ib, and then you get all the parameters you need for pulsing. Okay. So, once you know the calculations, then the power source can feed all the parameters and the wire feed rate to achieve the droplet transfer in spray mode at a constant arc length, right. It is clear. So, this is how we establish the welding procedures specifications. So, the money goes when you buy a power source and database for this, right. If some company, suppose if you approach us, so we need to develop a welding procedure parameter, and we will have to do all this exercise. If I want to weld say in a gas turbine component in GMAW in a pulse mode, then I will have to establish, because these materials may not be used or may not be developed, the welding procedures, and we will have to develop the welding procedures by following such principles to identify the stable metal transfer, right. So, that is a technology development, what do you call it. Yes, any questions so far? How do you arrive at the parameters, right. So, with this simple logic what we follow to identify the pulsing parameters for GMAW. Yes, it is clear, good.